African sleeping sickness is a parasitic pathogen transported into the humans from the bite of the tsetse fly. It kills thousands of people in sub-Saharan Africa every year and does this because it's a master of disguise, changing what it looks like to the host's immune cells to remain hidden and cause havoc in the host's body. Immune cells recognize all cells through interfacing with markers on the surface of all cells. These antigenic markers help immune cells identify what is friend and what is foe, and once the immune system has discovered an enemy, it is able to specialize weapons against the markers present on it. But T. brucei is a master of disguise and is able to change what it looks like to immune cells and evade destruction. A long-held belief about the variants of cell surface glycoproteins in T. brucei was that the main antigenic change was down to the sequence of amino acids in the change. This belief was largely due to the analysis of two different surface glycoprotein structures 3 decades ago. This study highlighted some conserved features between the structure of the variant surface glycoproteins. Two dumbbell-shaped lobes joined to form a heterodimer. We will refer to the part of the glycoprotein that faces away from the pathogen as the top, and that just makes things easier to talk about. From these studies, we were able to categorize variable surface glycoproteins into multiple classes, because scientists love categories. Class A, because it's the most sensible place to start, includes 3 different variable surface glycoproteins, named rather annoyingly VSG2, ILTAT 1.24, and VSG M 1.1, because being consistent is apparently beyond the scope of most biologists. Luckily, when this paper decides to show Class B surface glycoproteins, bless the lords, they name it VSG3, finally some consistency. Now I wonder what happened to VSG1. Anyway, back on track. As expected with Class B surface glycoproteins, the overall shape did somewhat match, but the underlying sequence of amino acids was different, so that must be what causes the distinct antigenic effect on these surface glycoproteins. Well, no. An analysis of VSG3 revealed that there was an O-linked glycan on the serine residue at position 317 on top of the glycoprotein, a glycan being a fancy way of saying a chain of sugar molecules. But how did they find this? Well, Sir Michael Ferguson had some words to say on this.
And then, because he's a very careful scientist, he's inspecting the electron density of the crystal structure that he's got, and he's assigning, where are the most electrons in this structure. And then what you do is you fit to that electron density map the amino acid chain of the sequence that you have, and basically you can fit your protein chain into that electron density map. And when everything agrees with each other, you know that's the right structure. Yeah. So he did that, and there was this little bit of additional electron density which was not accounted for by the protein sequence, right on the top level.
Yeah.
And because he'd done a really nice job of getting what's called a very high resolution crystal structure, I think 1.4 angstroms,
yeah,
that's pretty good. He was able to see that this funny extra bit of electron density looked like a carbohydrate ring, like a sugar ring, a glucose ring, an alpha glucose ring.
So of course, what did the researchers do when they discovered this? They injected it into mice, of course. They separated, it's not really called that, is it? A mischief of mice into 2 groups and injected one with T. brucei that had the normal wild-type version of VSG3, and one that had an altered version, not to contain this O-linked glycan. Results from this test showed that those injected with the wild-type died before the altered mice, even though most of the altered mice died after a while once T. brucei changed its surface glycoprotein anyway. The test, apart from showing that this pathogen can kill mice, also shows that addition to the O-linked glycan may play a role in the deadness of the pathogen. So what does this highlight for the study as a whole? Well, it highlights that we know nothing, as in there's still so much more to discover about cell surface glycoproteins that even to this day, 30 years later, we are still discovering new things.